In this module, we are going to discuss the application of binary integer decision variables. So let's first define what is binary variables. A binary decision variable can take a value of 0 or 1. Binary decision variables can be used to provide flexibility in modeling, especially in scenarios where the decision is about yes or no, on or off, and select or not select. For example, should I choose to apply to this college? If the answer to the question is yes, then we use 1 to represent the decision. If the answer is no, then we use 0 to represent the decision. Here are some additional examples, and you can see that the answer is binary for each of them, either yes or no. Let's see an example. Suppose this company is considering investing in several projects that have varying capital requirements over the next 4 years. And the management team would like to select the projects to maximize the profit while ensuring that the selected project will fall under the budget. So we can see that the decision is about whether to select each of the 4 projects. We can view this as if we are deciding whether we are going to say yes or no for each project. So let's define the decision variable xi as the binary decision variable such that xi equals to 1 if project I is selected and 0 if project I is not selected. Then we can write down the objective function as to maximize the total profit, where the total profit in terms of the present value is 90x1 plus 40x2 plus 10 times x3 plus 37 times x4. In this objective function, we can see that if a project I is selected, then xi equal to 1, and the corresponding profit will be realized. On the other hand, if a project I is not selected, then xi equals to 0, and the corresponding profit will not be realized. Next, we want to write down the constraints. Each year we have a limitation for the total capital. We need to ensure that whichever projects we select, there is enough capital to cover the capital requirement for the selected project. As you can see, the first year's capital requirement is 15 times x1 plus 10 times x2 plus 10 times x3 plus 15 times x4. And this total capital requirement cannot be more than 40,000 total capital that is available in year 1. Similarly, we can write down the capital constraint for year 2, year 3, and year 4. For each year's capital constraint, if a project is not selected, then its corresponding decision variable value will be 0, and the capital requirement corresponds to that project will not be counted. If a project is selected, then that project's capital requirement for each year will be realized. A feasible solution will need the 4 constraints to hold simultaneously. This is because when a project is selected, we need to ensure that there is enough capital to carry out the project for 4 years. Finally, we add the binary constraint to complete the model so that the solution for each xi is either 0 or 1. Then, we can use Excel solver to find the optimal solution. The optimal solution is to take project 1, 2, and 3 and do not undertake project number 4. And the maximum profit at the optimal solution is $140,000. Next, I want to talk about some other modeling skills using this example. Suppose we are choosing among 6 potential projects, And we use the binary decision variable xi to represent whether project I is chosen or not. Let's look at the first constraint. We want to make sure that exactly 3 projects are undertaken. Therefore, we can write down the constraint as x1 plus x2 plus x3 plus x4 plus x5 plus x6 equal to 3. If the constraint is changed to at least 3 projects must be taken, then we just need to change the sign from equal to greater than or equal to. If the constraint is changed to at most 3 projects must be chosen, then we just need to change the sign from equal to less than or equal to. Next, for the second constraint, we want to ensure that project 1 and 5 must be selected simultaneously. In other words, if project 1 is not selected, then project 5 cannot be selected, and vice versa. Similarly, if project 1 is selected, then project 5 must be selected as well, and vice versa. Therefore, we can write the constraint as x1 equal to x5. This is because when x1 equal to 0, x5 must be 0. When x1 equal to 1, x5 also need to be 1. In general, we will rewrite the constraint as x1 equal to x5 by subtracting x5 from both sides to get x1 minus x5 equal to 0. The reason is that by doing so, all decision variables are on the left-hand side, which is easier to input in Solver. Next, let's look at constraint number 3. Constraint number 3 says that either project 3 or project 5 must be undertaken, and project number 3 and project number 5 cannot be undertaken at the same time. Therefore, we know that exactly one of the 2 projects is selected, so we can write the constraint as x3 plus x5 equal to 1. Next, we consider constraint number 4. There are 4 possible combinations for selecting the 2 projects. The constraint says that project 1 cannot be undertaken unless project 4 is undertaken. In other words, if project 1 is undertaken, then project 4 is undertaken for sure. If project 1 is not undertaken, then project 4 may or may not be undertaken. And we can see that constraint x1 less than or equal to x4 will satisfy all feasible scenarios. And we can rewrite the constraint by subtracting x4 from both sides to get x1 minus x4 less than or equal to 0. Finally, let's take a look at constraint number 5. Constraint number 5 is actually the same type of constraint as constraint number 4, just with a different type of wording. If project 3 is undertaken, then project 6 must be undertaken. If project 6 is selected, then there is no limitation about whether project 3 is selected or not. When x3 equal to 1, x6 must be 1. When x3 equal to 0, x6 can be 0 or 1. Then we can see that x3 less than or equal to x6 satisfy all feasible conditions. By subtracting both sides by x6, this constraint can also be rewritten as x3 minus x6 less than or equal to 0. To summarize, if we are constructing a constraint to select exactly k subjects out of n subjects, then the constraint will look like x1 plus x2 plus xn equal to k. If we want to ensure that two subjects I and j are selected at the same time, then xi equal to xj. And we can also rewrite the constraint as xi minus xj equal to 0. If two projects I and j must not be selected at the same time, it means that at most one of them can be selected, and therefore xi plus xj will be less than or equal to 1. If exactly one of the two projects must be selected, then xi plus xj equal to 1. If subject I can only be selected if project j is selected, but not vice versa, then xi less than or equal to xj. The constraint can be rewritten as xi minus xj less than or equal to 0. These are the general rules, but actually you don't need to memorize everything. Just use your logic, and if you understand how 0-1 binary decision variable works, you can write out the constraint with the flexibility.